Heteroscedasticity is a problem in terms of the violation of one of the OLS assumptions necessary to conduct ordinary least square estimation technique. It refers to basically the variance of the residual is changing with the number of observations. So in terms of any estimation procedure, if the variance of the residuals is non-constant, then the OLS estimators are getting affected. And thereby the problem of heteroscedasticity arises, and it is more pronounced in case of a cross-sectional data. So when we are referring to the problem of heteroscedasticity, the first issue that crops in is a kind of a relationship between dependent and independent variable, and with the presence of an error term or a disturbance term. The OLS assumptions of the disturbance term refers to zero mean assumption, non-autocorrelation among the errors, and non-heteroscedasticity. But we observe that if the heteroscedasticity comes in, then the OLS assumptions will be violated and the estimators will fail the ideal properties. And thereby the problem needs to be detected, which can be done through graphical representation or scatter plots. And it is observed in case of a data where the variability can be due to changes in the level of income groups, or due to level of profits, or due to level of any other variable where the distribution is skewed. So among the different sources of heteroscedasticity, this is one of the major problems that crops in. Now the issue is that why the tests are required to detect the problem of heteroscedasticity. Because graphically the problem can be detected, but why we require a kind of a test procedure to go for it. So in case of any data analysis, we go for an inferential test procedure, and based on the inferential test procedure, it is important to identify the problem and the severity of the problem, because that requires confirmation. And thereby the test of heteroscedasticity tend to incorporate the basic idea of figuring out, which means that we are basically running an auxiliary regression. Auxiliary means a false regression is being carried out. And based on the false regression, we want to find out what problem is encountered and how the problem can be rectified. And thereby we can have a different kind of possibilities. Either a single variable is dependent for this error or for this problem, or there can be a combination of independent variables which may be actually involved here, either by its own effect or by the cross effects. So there can be different possibilities regarding the origin of the changing variances of the residuals. So thereby the tests of all heteroscedasticity continue to detect the problem and also give us the confirmation that the problem is existing. Though we can get the confirmation from the graphical representations, that is just an exploration, but the confirmation can be done through inferential test procedure. So basically we need to answer a set of questions. So in this particular slide, we actually want to seek answer to the first question, that does my model fit the data better in some places than in others? So it's a question of fitting the model when the problem is existing. And if the problem is existing, how can I adjust my procedures, or how can I adjust my estimation techniques without deleting the observations or without throwing away the data set? Secondly, the question on the overall significance of the model. So in a normal OLS method, we observe that the overall significance of the model is explained by the word goodness of fit. That is, what is the percentage of explained versus unexplained. That is the proportion of explained sum of squares in total sum of squares compared to the proportion of residual sum of squares out of the total sum of squares. So if the explained proportion is higher, then definitely the model has a better goodness of fit. So we want to find out whether the goodness of fit is better at low values or at high values. Because if the goodness of fit is changing, definitely the R square will be changing, and definitely the problem is existing. So all these questions are going to identify the degree or the intensity of the problem of heteroscedasticity, and thereby the test is required to understand its severity and also to make a confirmation about the presence of this problem. So basically we want to go for two important ideas. First of all, the problem needs to be defined in terms of changing variance. Then we want to explain in terms of the detection of the problem, which can be done to graphical plotting. We need to identify the source of the problem from a theoretical perspective. And then we have to actually convince that why the tests are necessary to be conducted in this case. The tests are necessary to be conducted to confirm the presence of the problem regarding the changing errors or the changing variances, and also how the problem can have a confirmation after the test being conducted, and thereby we can actually propose any kind of suitable estimation procedure. So this calls for the test of heteroscedasticity to be discussed in details. Now we actually focus on the test for heteroscedasticity, because any one of the violation of the OLS assumptions call for a confirmatory test. So among the OLS assumptions, we find out the problem of changing variance, the problem of serial correlation among the errors, and the problem of multicollinearity. So if any one of these assumptions are violated, or if this problem exists, we need to have a set of tests to identify the problem and to understand the severity and to have a confirmation on them. So thereby we look for the test for heteroscedasticity, and firstly we go for the graphical plot. Graphical plot basically refers to clustering of observations, and secondly we go for the inferential test. In the words of statistics, any inferential test requires setting up of a hypothesis. So hypothesis can be of two types. It can be null hypothesis, where the problem is not existing, which is actually to nullify. And the second one is an alternative hypothesis, which calls for the existence of the problem. So based on the statistical significance of the test statistic, we arrive at a decision rule whether the null hypothesis will be accepted or rejected. If the null hypothesis happens to be rejected, then definitely the problem is existing, and this is the confirmation we expect after conducting any sort of inferential test procedure. So here we look for the graphical plots or the graphical representation. Graphical plot basically refers to a scatter plot where we observe the detection of the problem, and in case of the heteroscedasticity problem, we find out the clustering of points is actually coming up, which is very much relevant in case of any cross-sectional data where for a particular income group, maybe the spending will be very high for the high income groups, or for the low income groups in a sample, the spending may be very low. So we can have two distinct clusters in the set of observations, and accordingly the variance will be differing, because the variance will be high for the high income groups and will be less for the low income groups because they have limited choice. So depending upon the availability of choices to a rational consumer, the variability of the spending will depend, and that will be reflected in the error terms or in the residuals. So this is very much relevant in case of clustering of points or clustering of observations, and so it is highly pronounced in case of a cross-sectional data. Secondly, when we go for collecting a sample from a heterogeneous population where different kind of spending habits arises, different type of lifestyles exist, then also the variability comes in. If the data is also collected from the companies which shows different levels of dividend policies based on their profit margins, there also the heteroscedasticity problem is very acute. So in all these examples, we observe the cluster of observations coming in, and thereby the problem comes in. Even in the time series data, if we deal with the daily data, particularly the frequency of the data matters when we are actually taking a data which keeps on changing with time. For a time series data, if it's an annual data, then the problem of heteroscedasticity does not exist at times. But in case of a daily data or a weekly data, for example, stock prices, for example, exchange rates, we find out that the heteroscedasticity is an acute problem, even though the data is a time series data, because we observe the fluctuations which may be high in one day or may be high in 2 days in a week and might be less in the other days of the week. because of a number of external and the internal factors. So in all these cases, the problem of scatter plot will come up and thereby the clustering may be observed. But this is just an exploration. We need to justify the exploration by conducting a set of confirmatory tests which calls for the test of heteroscedasticity. So in this particular slide, as we continue our discussion for what are the tests for heteroscedasticity, we start with the first test, which is called Goldfeld quant test or GQ test. This test is one of the most popular tests and it can be done in any one of the updated softwares that is available in econometrics today. Even it can be done in Excel. We observe the n number of cases which are collected for a variable x. X can be consumption expenditure, X can be personal savings, which may be correlated with the EI square. EI square is basically the variance of the error term, because the error term is defined by E and we make a square of that, because error term is basically the difference between actual value and the predicted value. The difference can be negative or can be positive. So to get rid of the negative terms, we square it up and we get EI square. After that, what we do, we actually concentrate on the extreme section of the data set. So what we do, we drop a section of the middle level of observations. Like 1/5 of the total number of observations is dropped. It is actually called slicing of the observations. So we take the upper slice and the lower slice. For example, we run a separate regression for the upper and the lower samples. Because if we conduct the income consumption relationship, we will observe that for the low income groups and for the high income groups, the variability will exist. So we are not interested with the middle income groups, but we are interested about the lower and the higher income groups where the variability will change. And accordingly, we do separate regressions for them. And we compare their respective goodness of fit. So goodness of fit for the upper income in compared to goodness of fit of the lower income. So in this particular slide, we observe that there are 4 distinct steps. The first step is we are going to take up the data and we are going to arrange the data in terms of the correlation with the variance of the error term, basically in an ascending order. Then we drop the middle level of the observations and then we concentrate on the upper and the lower sections as the variability will come up. Next, we move on to how to conduct the test statistic. The test statistic will be based on separate regressions to be run, and these 2 regressions will be compared. So basically, we are actually interested to find out residual sum of squares from each of them. And thereby, it can be done only by estimating the ESS, that is explained sum of squares for 1. 1 means the upper end or the lower end as we choose. Say ESS 1 is for the lower income group and ESS 2 for the higher income group. Separate regressions were run and thereby we go for comparing their variances, which means it is the ratio of the variances of the 2 distinct sets of regressions, which we refer as GQ, which is Goldfeld quant test statistic, which has an F distribution because it's a ratio of chi-square distribution ending up with a F distribution. So for F distribution, we have 2 different degrees of freedom where N1 minus K1, N1 stands for the number of observations, K1 stands for the number of variables to be estimated. Similarly, for the second set of regression, N2 minus K2. So these are the 2 distinct set of degrees of freedom applicable for 2 different variances. The ratio of the variances is done and thereby the GQ test statistic is computed. Now we go for how the interpretation is to be done. So first of all, we look at the expression of the test statistic in this slide, which is GQ, sigma 1 square by sigma 2 square. So we will be concentrating on the numerator and the denominator separately. So here we concentrate mainly on the first regression, which is being done for the higher income groups, which is given by ESS 1 by degrees of freedom. So the degrees of freedom is, as it is seen, number of variables minus the number of estimators. So as a result of that, the first regression is done for the sigma square 1, which is given as in the numerator of the GQ coefficient. Secondly, we move on to the next slide, where we basically concentrate about the denominator. So in the denominator, we refer to sigma 2 square, which is referred to the second subset, which is on the lower set of observations on the lower group, and thereby for this a separate sigma 2 square is conducted. So finally, we see that if the GQ test statistic is significantly greater or lesser than 1, that means we go for a value which is either increasing the unity or less than the unity, then definitely the null hypothesis is actually violated, and we have the evidence of heteroscedasticity problem. So that means if the test statistic appears to be greater than unity, which means that under the null hypothesis, there is no significant difference between the variances of the lower income group or the higher income group or any two sets of regressions. So there is no significant difference between any two set of regressions in the null hypothesis, but the alternative hypothesis is contradicting that there is a significant difference. So in terms of the statistical values, after the test is conducted, if the GQ test statistic is significantly greater or lesser than 1, then we will reject the null hypothesis and we will confirm that the problem of heteroscedasticity or changing variance is present. And thereby the Goldfeld-Quant test is the most popular and more convenient way to actually detect the problem of heteroscedasticity under inferential testing. Similarly, we can go in for more other tests to check the robustness of the Goldfeld-Quant test. Because in any data analysis, we need to conduct more than one test to confirm the severity of the problem. Because we need to identify the source of the problem. That is, what is responsible for the problem, which variable is responsible for this heteroscedasticity. So that can be explored if we want to conduct more than one test. So now we go for the second test, which is basically the Gleiser test. So the Gleiser test basically says that we perform the residuals and we save the residuals. So any kind of regression analysis will be actually generating a set of residual series. The residual series needs to be saved. And now we look at the absolute value of the residuals. That means we know that residuals can be negative or positive, but we do not square it up. We look at the absolute value by ignoring the minus sign, and thereby we go for a significant coefficient of this ui hat, which is written within the modulus, will be indicating the severity of the problem. That means if the test statistic happens to be significantly different from 0, or it is higher than the table value, then definitely the null hypothesis of non-heteroscedasticity will be violated, and thereby the problem will be existing. So this basically refers to a significant coefficient of the error term, and thereby the absolute value will be taken into consideration. So in the Gleiser test, we actually want to examine which variable is responsible for this problem. Either one of the independent variables is actually responsible for this problem, and that is what we actually want to estimate in this particular test. So Goldfeld-Quant test actually goes for the observations, which are actually ordered in terms of the groups, but the Gleiser test is identifying a variable responsible for the problem. Either one variable or a group of variables may be responsible for this absolute value of the error term, which is significantly different from 0 or not different from 0. Another robust test to confirm both Goldfeld-Quant and Gleiser is the White test. Because White test is the most robust test among all, because White test actually explores all the possibilities for this problem. Why we are saying all the possibilities? Because it looks into the independent variable not as a single variable, but there may be interaction among the independent variables. For example, there is a study on wage and education. So wage of an individual is dependent upon the education of the individual, but the education of the individual is one of the independent variables. Another independent variable may be the parental education. Another independent variable may be the proximity of his place or residence to the educational institution. Another can be any kind of family upbringing, that also is one of the major variable affecting his education. So there can be interaction term between the father's education and the upbringing in the family. Because if there is an educated family, then there is a general tendency that education will be imparted to that particular child. So all this can have an interaction effect on the wage. So accordingly, all these possibilities are there in a cross-sectional sample, whether the cross products also are responsible for this problem. So to explore all these possibilities, White test is one of the strong tests to detect the problem of heteroscedasticity. So in this particular slide, we observe for the White test, the first step is regress the squared residuals on the dependent variable. So we observe a residual series, and since the residual series can be negative or positive, we do not take the modulus, unlike the Gleiger test. We take the square of the residuals, that is EI square. Now this EI square is now treated as a dependent variable, and it is regressed on all the independent variables we have, not only own terms but also the interaction terms. For example, we take all the x variables, x1, x2, x3, like father's education, like parental education, specifically upbringing in the family, or the family's income status, or the proximity of the educational institute to his place of residence. All these are separate independent variables taken. Cross terms means the interactions are taken, multiplicative form, and also the square of the x variables. The relation might not be always linear. It is said that always in heteroscedasticity we have a linear relationship, but might not be linear, it can be non-linear. So we explored that possibility also, that square of x variables. So it's a long equation where we have own terms, cross terms, and also the non-linearity in it. So on the basis of this, we basically go for a Lagrangian multiplier test, which we call LM test. So a Lagrangian multiplier test statistic is taken up, which is n into r square, a simple expression. N is a number of observations. The star stands for into multiplicated by r square, that's the goodness of fit. And now this LM test statistic follows a chi-square distribution because it's a non-parametric test. It has a non-linearity in its equation. So depending on that, the LM test statistic comes in. So if the LM test statistic is significantly different from 0, or the computed value is exceeding the table value, definitely the null hypothesis is violated and the problem of heteroscedasticity is there. So actually White test is robust and it is preferred to all the other tests because it does not assume a relationship between x and the variance of error term. That is no monotonic relationship, one-way relationship. It takes care of all the possibilities that is possible, also takes care of non-linearity in the relationship, and so this test is the most popular test to conduct for heteroscedasticity. So here we observe that the three tests are the most popular tests which are conducted. Firstly, the Goldfeld-Quant test, which only takes care of the order of the observations, and we are only looking about a part of the observations, not the entire one. In case of the Gleiger test, we look at the absolute value of the error term and we do not ignore, or we take care of only that particular set. But for White test, we not only consider the entire observation, but also we look at various functional forms, and also we look at the interaction terms. So White test is one of the most popular, one of the strong tests to identify the problem of heteroscedasticity. And also in the White test, we go for a kind of a Lagrangian multiplier test, which says whether the null hypothesis is accepted or rejected. So among the three tests, white test is preferred to all the other two, and thereby the problem needs to be detected after inferential testing. After conducting the test for heteroscedasticity, and if the null hypothesis gets rejected and the problem is existing in the data set, we need to propose estimation procedure other than ordinary least square. Because ordinary least square is based on the satisfaction of the OLS assumptions, and if the problem is existing, that is the problem of heteroscedasticity, where the variance of the residuals keep on changing, then we need to devise an alternative test procedure. And this calls for what are the estimation procedures under heteroscedasticity. So actually we propose to go for generalized least square or weighted least square instead of ordinary least square. So this generalized least square is basically based on a weighted way or weighted mechanism which is added on the residuals to take care of the problem. It's not that the problem will be eliminated or the data set will be thrown away. The data set will be kept in the form accepting the existence of the problem, and thereby the method of estimation will be proposed. So it is basically being done under two definite cases. When the sigma is completely specified, that we are aware about the origin of the problem, which variable is responsible for the problem, so we can go for a correct diagnostic mechanism. So we can have a correct diagnosis of the problem if the problem is known, or if the problem is unknown, how can also the diagnosis be done? So the diagnostics of the post-estimation results means that accepting the presence of the problem, what kind of remedial measures we can suggest, or what kind of proper diagnosis can be done when sigma is specified or sigma is unspecified. So invite two cases. Case 1, when the sigma is specified. So in this particular slide, we refer to a number of steps. Like in step 1, we start with our basic multiple regression model where we observe yi is the dependent variable, xi2 to xik, because it's a k variable multiple regression model with the presence of a disturbance term epsilon I, and betas are the slope coefficients from beta 2 to beta k, which has a k cross 1 dimension, and beta 1 is the intercept. Now we go to step 2. Because we understand that basically sigma I is known, the problem is identified properly, it is specified. So we divide both the LHS and the RHS by the sigma I, and the problem is known. So we basically deflate the entire equation by sigma I. And thereby we go for the step 3 where we observe that this error term which comes up at epsilon I star is basically epsilon I divided by sigma I. So what is this? This is a new error term being generated after the deflation is being done by sigma I in step 2. So in step 3 we define a new error term sigma I star, which is none other than the last term under step 2. So we know by the OLS assumptions that variance of sigma I star is 1, because sigma I square by sigma I square cancelled out and we get a constant variance, and the zero mean assumption. So based on these two OLS properties, we can now say that OLS can be applied. So if the sigma is specified, the most easiest way is to rectify the problem is by dividing the equation of sigma I and thereby deflating by sigma I, and we are getting a new error term which is the original epsilon I divided by sigma I. We calculate the variance of the new error term, and thereby we actually come to the conclusion when the variance is constant and OLS can be applied when the sigma is specified. Now we proceed for the second case when the sigma is not specified. So if the sigma is not specified, then we observe that there may be some kind of possibilities that sigma is directly proportional to the square of the independent variables. So this problem is just a kind of an intuition, a kind of a conjecture, a guess that might be sigma square is directly proportional to the square of the independent variables, because if the square of the term rises, the sigma square also changes. So what we do? We divide the entire equation by xij square, and that is what the deflation is being done, and then we can apply the OLS. So in this particular model, we find out that in step 2, we address the nature of the relationship where sigma squared is directly proportional of xij square. In step 3, we identify the origin of the problem, which is just a conjecture, a guess. And after identifying it, we are dividing the entire equation LHS and RHS by xij square, because that is what the deflating is being done. And thereby we can apply the OLS. So OLS can be applied provided the last term is giving us a constant variance. So thereby in these two cases we observe that depending upon the nature of the problem, the rectification can be done, but here we can apply the GLS provided that the weights are being taken up, and thereby we can go for the ordinary method. So to sum up this particular discussions in this particular module, we observe that the detection of the problem can be done graphically. That's an exploration. But after that, we need to conduct some test where Goldfeld-Quant test is the most convenient way to do. But White test is one of the most robust tests, which is an advantageous over the two tests like Goldfeld-Quant and the Glaser test, which calls for the confirmation of the problem. And after the problem is confirmed or the null hypothesis is rejected, we need to propose an estimation procedure to rectify the problem, that is a remedial measure. So the remedial measure refers to a generalized least square technique where the origin of the problem needs to be identified. Accordingly, the weights will be assigned, and then we can get back to the fulfillment of the OLS assumptions. So that is how the estimation under heteroscedasticity is being conducted.